The second example of a mirage is a floating boat. So this is a real photo taken by a person in the summer in the beach. So you can see that the boat now in the photo, it seems it is floating in the air. And how could it be possible? What is the explanation for that? So remember, this is in the summer. So what happens is that, let's try to think that this is the location of the boat. So the light will come from the boat. So the different thing compared with the first example of the mirage is that in the desert, the surface of the land is very hot. But now the boat was on the surface of the ocean that the air is cooler. And actually, the surface of the air is cooler than the upper level of the air there. So what happens is that when the light propagates, the light is entering from a denser media to a warmer, which is the less denser media. So therefore, let's try to think about that. The light interact with the surface here, and this is a normal line. The dashed line is here along these directions. And from a denser media to the rare denser media, what does it mean? Which means the velocity will entering from a region with the slower speed of light to a fast speed of light. So the light will be bended away from the normal line. Yeah, they will be bended away from the normal line. So they will keep bended. And when the light entering to your eyes, it is complete bended, and they will give your eye an illusion that the boat is actually from these directions. So this explains that why the boat origin should be here, but because the light was bended when they enter into your eyes, the image is here. That is the second interesting example for the mirage. And now in the daily life, when you are swimming in the swimming pool, when you try to take in a picture for a person with the image above and below the water, you will see that this kind of the distortion of the image. It seems that the head was cutting off by the body, but apparently it is not possible. Yeah, so it is definitely also due to the refractions, because the image from the head here, it is not reflected when they enter in your camera, but the body is. But personally, when I find this photo, I think that this kind of the difference, I would suspect this one is due by Photoshop. This one is more likely, and this is probably done by Photoshop. But no matter what, I just give you a sense of feeling that the concept of the reflection is everywhere in our daily life. Now I'm going to study a very extremely case for the reflections. So now let's try to focus on the scenario. A light enters to a medium with a lower index of refractions. So what does that mean? So you can think about that the original light was in the water and entering to the air in this case. So apparently it will be bended away from the normal line, as I keep saying before. Yeah? And this refraction is still obey the Snell's law. So if you keep increasing the incident angle theta 1, you make it bigger and bigger, for sure theta 2 will become bigger and bigger. Yeah? And people find out that if you make the theta 1 bigger enough until some value, which is called the critical value, theta 1 equal to the theta c, then the angle of the refractions will be 90 degrees. So what does it mean? It means that any theta 1 which is bigger than theta critical, they will be completely or totally reflected. So there's no light will be reflected. This is a very unique scenario. So this angle, for sure, it depends on the index of refractions. But let's try to define this theta critical. So this theta critical happens is that when you use the Snell's law, and the incident angle is 90 degrees. And this is the angle of the refractions, and this is angle of refraction. So let me correct that. The angle of the refractions is 90 degrees, and this is the angle of the incident angles. So the critical angle is the incident angle. And this one happens is that when you substitute this value for the refraction angle with the index of the refraction n2 in the Snell's law, you will get this value. So why I'm going to introduce to you the concept of the total internal reflections, because there are several very interesting applications, and one of the interesting application is optical fibers. This will be a very useful application when people try to communicate in the future. So what is the optical fibers? They are the thin fibers composed of the glass or the plastic core with a very high index of the refractions. They're surrounded by a outer layer coating or the cladding. And this kind of coating has a low index of refractions. So which means that the center with a high index of refraction and the surface with a low index of refractions. So the light which is introduced into the core of the fiber at one end, and it then will be propagated along the fiber in the zigzag path. So like the path I show you here, zigzag path. And undergoing a one total internal reflection after another. So every time when the light hit on the surface, because of index of the difference of index of refractions, every interaction is a reflections. There's no refractions. So this is a total internal reflection for every single interaction here. So therefore, the core is so transparent that even after the light propagates through 1 kilo length of the fiber, the amount of absorptions is roughly the same as if the light has simply passing through a glass window. So which means this is a very efficient way, a wire to propagate the light, which is the information. And here I show you the true situation in lab. So you have the light source, and the light source propagate along the so-called optical fibers. And you see, no matter how the optical fiber is bended, the light only will be propagated within the wire or the fibers and going out from the other end of the fibers. And don't forget about that. The information, the message propagated here through the optical fibers is still in the speed of light. So now let's finally have our first conceptual quiz today. So now, when you try to shoot a fish by a gun, how should you aim at the image? You should aim above, below, or at the image. So remember that here, you are trying to use the bullet, which is not a light. But the fish, the image you see, is a light. So think about this one carefully. And the answer is C, because the image you see actually is, the image you see is here, but the real fish is here. Therefore, you should try to aim at lower below the image. So which means when the bullet comes, they should come here directly. If you aim at the image directly, they will hit the image directly. So now let's have the second conceptual quiz. Now you try to shoot a fish with the laser gun. Then where you should aim at? So remember that this is the image you see of the fish, and also you're not using the bullet anymore. So this is a tricky one, so think about it carefully. So the answer is A, because the laser beam will be bended when it enters into the fish. So now, even though the real fish is here, this is the image you see. But now if you aim at the fish, the image of the fish, you still can hit the fish, is because the laser beam will still be bended and hit the real fish in the case. So you can see now the difference depending on you're using the bullet or the laser beam. It is a source different, yeah? Now, another very interesting example is the Brewster angle. So what is a Brewster angle? it is a particular angle that light reflected is totally polarized. So in the chapter 25, I introduced you that how do we define the polarization of the EM wave. And now here, for this particular angle, when the light interact with the surface, you will have the reflected light and the refracted light. Reflected and reflected. So in the case, you have two different angles. The theta B is the angle of the reflections, and theta 2 is the angle of the refractions. And the relation between the theta B and theta 2, they still obey the Snell's laws. Yeah? So n1 multiplied by the sine theta B is equivalent to n2 multiplied by the sine theta 2. So why this angle is so interesting is that when this polarization happens for the reflected light happens, the submensions, actually, I should say that is that the angle, the direction of the reflected light is perpendicular to the direction of the refracted light. So it is perpendicular to each other. And did you see that this is a normal line? Yeah? So what does that tell you? If these two directions are perpendicular to each other, it means that the summation of the three angles, theta B plus the 90 plus theta 2 is 180. So let's take a look about the diagram again. If you sum theta B, 90 and theta 2, it is 180. And for this kind of particular scenario, the reflected light will be polarized. And what is the direction of the polarization? It is parallel to the reflecting surface. So it is parallel to the reflecting surface. And this is a very interesting property. So therefore, we are going to define the so-called the Brewster angle, theta B, in terms of n2 divided by n1. But actually, this is not simply a definition. There's a reason for that. So if you take a look about the sine theta 2 are used in the Snell's law. What is theta 2? It is refracted angle. Yeah? So the sine theta 2 actually is 90 minus theta B. You will say why? Let's take a look about this formula carefully. So if you subtract 90 on both ends, so theta B plus theta 2 is 90 degrees. Agree? Then that's the reason theta 2 is 90 minus theta B. And from the trigonometry relation, then you will find out the sine 90 minus theta B is actually cosine theta B. So now let's substitute sine theta 2 by cosine theta B. So sine theta 2 is cosine theta B now. So therefore, if you divided cosine theta B on both ends, you will become tangent theta B here. So n1 tangent theta B is n2. So therefore, tangent theta B is n2 divided by n1. And this is the famous Brewster angle.